So the next question is, the rate constant for the first order decomposition of H2O2 is given by the following equation. Log K equals to 14.2 minus 1 into 10 raised to the 4 Kelvin over temperature, and we have to calculate E0 and rate constant K, which is this, if it is given that T half equals to 200 minutes, and it is also given the value of R equals to 8.314 joule Kelvin inverse mole inverse. So let's proceed to the solution. We know the decomposition of H2O2 is as follows. So this is the decomposition of H2O2 reaction, and we also know that log K equals to log A minus EA over 2.303 RT. So we know this equation, log K is equals to log A is the activation energy, minus EA over 2.303 RT. So now we can compare these two and find out the required values which we have defined, E0 and constant K. So this EA over 2.303 R equals to 10 raised to the power 4. So we get that EA over 2.303 R equals to 4. So now activation energy we can find from this, EA equals to 10 raised to the power 4 into 2.303 R. This is the activation energy, and the value comes out to be 19.14 into 10 raised to the power 4 joule mole inverse. So yeah, so we knew that log for any equation or any chemical reaction, we have log K equals to log A minus EA over 2.303 RT. We compare it with the given equation and we find out the value of EA, that comes out to be 19.14 into 10 raised to the power 4 joule mole inverse. So now we have to find the value of K if T half is given as 200 minutes. So as we note that K is 0.693 over T half. We know this equation, K is always equals to 0.693 over T half. So we put the values and we find that K is 5.78 into 10 raised to the power minus 5 second inverse. So this is the value of EA and so K goes to 0.693 over T half, and T half is given as 200 minutes. From that, the value of K comes out to be 5.78 into 10 raised to the power minus 5 second inverse, and we had calculated the value of EA here. So the next optional part of this question is, write the mechanism of free radical polymerization of ethene. So we know that in the free radical polymerization of ethene, there are basically 3 steps. The first one is chain initiation. The second one is chain propagation. And the third one is chain termination. So these are the 3 steps involved in the free radical polymerization of ethene. So let us see how in these steps the reactions occur. So in the chain initiation step, basically we have the benzoyl peroxide, which is the initiator. So benzoyl peroxide is C6H5. So it is the initiator and it is benzoyl peroxide, and it generates the free radical which initiates. So the free radical formation so it leads to the generation of the free radical, which is the phenyl radical here. Now this phenyl radical propagates the chain. We will see how it does so. So C6H5 phenyl radical, it reacts with ethene and it forms this as the product. So the free radical which was formed in the chain initiation step, phenyl radical, it reacts with ethene, it attacks, and we get this free radical. So now the chain termination can occur as follows. So here it is, the chain is getting increased with each ethene it adds on. And the termination so on termination we get finally the polythene polymer. So the 3 steps we can see: the chain initiation, here benzoyl peroxide leads to the formation of phenyl radical which attacks on ethene molecule to form a free radical which grows on with further addition of ethenes, and finally it terminates by joining of by adding of 2 free radicals, and we get polythene polymer. So the next question is the first part. Calculate E naught of the cell for the following reaction at 298 Kelvin, and the reaction is 2Cr in solid state plus 3 Fe2 plus. The molarity of Fe2 plus is 0.01 molar, and it gives 2Cr3 plus. The molarity of Cr3 plus is 0.01 molar and 3 Fe solid, and it is given that the E of the cell is 0.261 volt. So as we know that E cell is equals to E naught of cell minus 0.591 over n log 10 concentration of product concentration of reactant. So yeah, E cell is E naught cell minus 0.591 over N into log to the base 10 concentration of product over concentration of reactant. So here N is basically the number of electrons being exchanged in the following reaction. So here we can clearly see that 6 electrons are being exchanged in the reaction. So the value of N equals to 6. Now we can see E naught of cell should be E of cell plus 0.591 over N, and N equals to 6 into log to the base 10 concentration of product over concentration of reactant. Now let us solve these. Because we have the concentration of product, it is 0.01 molar, and concentration of reactant, it is 0.01 molar. And we can clearly see that since Cr in the reactants and Fe in the product are in the solid state, so the concentration, their concentration do not affect this reaction, this equation, and we do not take the concentration of only these ions in the solution. So we can put the values here. E of cell is given as 0.261 volt plus 0.591 divided by N, that is 6, into log to the base 10 0.01 raised to power 2 over 0.01 raised to power 3. So because the numerical coefficient before the reactant of product, before the product here is 2, so the concentration raised to power 2, and here the numerical coefficient is 3, so the product of the concentration of reactant raised to power 3. So we get this. So finally solving it, we get 0.261 plus this is evaluated as 0.009 into log to the base 10, and it is 10 raised to power 2. So since log 10 to the base 10 equals to 1, log 10 raised to power 2 to the base 10 will be 2, and so the answer would be 0.261 plus 0.009 into 2, and the answer is 0.2806 volt. So we finally get E naught of the cell as 2.80. So the next part of this question is using the E naught values of A and B. The E naught values of A and B are given. E naught value of A is minus 2.37 volt and E naught value of B is minus 0.14 volt. So using the E naught values of A and B, predict which one is better for coating the surface of iron, and the E naught value of iron is given. So the E naught value of iron is So seeing these three E naught values, we can clearly see that A is the most reducing. So since A has the least reduction potential, that is A has the maximum negative reduction potential, so A can be used to coat the surface of iron, whereas B cannot be, because B has less negative reduction potential than iron itself. So we need a compound which has a reduction potential more negative than the reduction potential of iron, which is A. So A can be successfully used to make the coating of the surface of iron to prevent its corrosion because A has more negative reduction potential.